So let me first start by thanking since I'm also technically one of the organizers, so I have to thank the super organizer for the invitation to speak here. And also thank Nadi for what must have been a very painful experience sitting through all these talks and pretending to care a lot about them. So yeah, we're almost done, and I'm sure you'll think twice about turning 60 again. So I think I'm the last student to go. And I'm also I think I'm the only student to have gone into particle phenomenology primarily. So, so I'm going to make just a few comments. Well, actually, I'm going to make a few comments about things that have already come up, and then comment about Nadian phenomenology. So that's all before the scientific part of the talk. So one issue that's come up already is the unreliability of history and memory. And this was recently, this exact anecdote about the bug in the seminar room was recently brought again to my attention. And one thing that was missed, I think, in the previous iterations of the story in the morning was that there was a postdoc, a phenomenology postdoc actually, named Human, who's now at Brookhaven, who was the one who gets the credit apparently for shouting out, "Why don't you crush it, Nadi?" But then recently, I've heard from a young postdoc here that somehow the story has changed over the course of time, and now it's me who was the one saying that. So just to correct the record, I did not go there.
A lot of the other elements are also not true. In fact, there's so many versions that underscores the fact that our memory is important.
I don't believe anything that happened in history anymore. Based on this. Yeah. Okay, so that's just one comment. Now the second concerns a story, which I guess, so I started working with Nadi in 2002, and as you know, he likes to give his students trial projects where he decides whether they're fit to work with him or not, and it's always phrased like, oh, it's not about, how good you are as a physicist, just whether we're compatible, at a personal level or something. So anyway, I was given some projects about the D0, D4 system and non-commutative geometry and instantons, and I toiled away at it, and I was appropriately terrified and stressed out. And then I made some progress, and one day Nadi said, you passed, you passed the trial project. Congratulations. And then shortly after, I was actually wearing this t-shirt, which is, I don't know if you could see, but it's a shirt of Orson Welles from The Third Man. And I knocked on Nadi's door to ask a question or something, and he saw me wearing this t-shirt, and he's like, oh, if I knew you were a fan of Orson Welles, I would have taken you on as a student immediately. So from this, I learned that Nadi was not this super physics machine, but was a human with a sense of humor and a love for old movies. No, this is actually from the Brattle Theatre in Cambridge, so you'll have to go there to get that. Yeah, so I learned Nadi loves old movies, and I think one time I told him I didn't think that highly of duck soup, and I went down several levels. I went down several levels in his esteem, so I'll try to make up for that in today's talk. The other thing is I learned Nadi had a sense of humor, how good you could debate the jokes are, but that reminds me of another story. When I was a postdoc, I think Nadi told some horrible joke, and I offered my opinion that maybe we're contractually obligated to laugh at his jokes if we work here. And Nadi immediately said, well, you're contractually obligated actually to tell worse ones. So I'm going to work on that in today's talk too. Okay, the last thing I want to comment on is if you actually, I didn't realize this, but I went back to look at Nadi's 200 or so papers, and I noticed there's an interesting periodicity. There's an interesting pattern, which I like to think of now as Nadi has a 10-year itch, and that's a 10-year itch to work on particle phenomenology. So I actually pulled it up here. So the first time this happened, I guess, was at the beginning of Nadi's career. Starting in 1981, Nadi built some models for composite quarks and leptons, and then went on to do his amazing work, first of amazing works in SUSY QCD. So that was in 81. And then in 92 or so, There were these papers that have been referred to already on flavor models and supersymmetry, which I'll actually refer to again in today's talk. And then roughly 10 years later was the work that we did together starting in 2006, here, and continuing for another few years. And so it's 2016 now, so I look forward to Nadi coming back to work on particle phenomenology again within the next couple of years, which, maybe they'll discover something at the LHC to match that pattern. Is there a pointer here? Oh, okay, great. Okay, so the last thing I want to comment on is how I got into phenomenology, and it goes without saying that, Nadi has had a huge impact on my career, on my life. Apart from my parents, probably the biggest impact anyone's had. And it was in 2005 that, yeah, I think so. Oh, maybe not.
There's a thing on the side to turn it on.
Okay.
Okay, I see it. Okay.
Got it, okay. So in 2005, I think Nadi and, let's see who the organizers are. Nadi and Chiara, I think, and Igor organized the PITP school, which was for the first time on collider phenomenology. And this was because the LHC was about to turn on. It was supposed to turn on in 2008, and then there was that accident, so it got delayed for a couple of years. The excitement was in the air. We heard already from Nima about the LHC Olympics and how we were going to discover all these new particles at the LHC. And so I got infected with this enthusiasm, as did, I think, a lot of people here at the IS. And I want to call your attention to, there was this practicum on simulations run by Konstantin, where I have a distinct memory of Edward trying to install Pythia and asking where his home directory was and where the Pythia was sitting inside the home directory. So that was an interesting time, and it's because of Nadi's influence. He saw early on what a big deal the LHC would be, and I didn't see that coming at all, being a student still, but I followed Nadi's suggestion and haven't stopped really working on LHC physics since then. So that's what I want to tell you about in today's talk. Now, okay, so the title of today's talk is Natural SUSY versus the LHC. This is work I'm doing in collaboration with my excellent collaborators at Rutgers, Matt Buckley, his student David Feld, my student Sebastian Macaluzzo, and our postdoc Angelo Monte. And what we're doing is we're reinterpreting all of the latest LHC results and seeing what they imply for supersymmetry, and specifically natural models of supersymmetry. And why am I so focused on supersymmetry? Well, this was sort of the initial condition given to me from that PITP school in 2005. And I still think it's they're the usual motivations of naturalness, which we'll be focused on today. There's unification, there's dark matter, so there's all these reasons. And I think these reasons are shared by the many people in the audience, including Nadi. Although if you ask him these days, he's probably more likely to vote for a complete surprise or nothing at all at the LHC. But probably among all the things we know about, all the ideas that people have had, supersymmetry is probably still the most likely, with a low absolute probability, but a large relative one. So certainly, Nadi has worked, as we all know, he's done all these amazing things in SUSY QCD and in supersymmetry more generally, SUSY gauge theories. And while they're all sort of the amazing results, non-perturbative results, and formal study of these supersymmetric gauge theories, it would also be really nice, although not necessary, but it would be really nice if they were realized in nature. So that's another motivation for natural SUSY at the LHC. And so I'm sure Nadi would it would have been nice to present Nadi with the 60th birthday present, which is the discovery of supersymmetry, but I think we might have to wait another 10 years for that. So this talk could have also been called Nadi versus the LHC. Okay. All right. So let me begin with the scientific part of the talk. So since 2010, as I'm sure you've heard, the LHC has been performing spectacularly. Time has gone by very fast, and with it, the LHC has improved at every iteration. These are the 4 different runs, essentially, that we've had, one every year. And you can see this is the integrated luminosity, the size of the data set, versus time, and you can see that the slope is generally increasing, meaning that we're on some faster than linear growth of the data, not to mention the doubling of the energy that happened last year. So this is where we are now, roughly, and at about 30 inverse femtobarns per experiment. And what was presented recently at ICHEP is about half that. So they're sitting on twice as much data already. So as you know, at run 1, the principal positive result was that we discovered the Higgs at a mass of 125 GeV. And now it seems, by all accounts, to be fairly standard model-like. In the early days, there were some interesting fluctuations, but things are more or less regressing towards the mean, which is the standard model prediction. And before we discovered the Higgs, well, there was debate about whether it even existed, but certainly there was no idea about what its mass was, other than that it should be heavier than the previous limit, which was 114 GeV. So now we know the mass very precisely. It's 125 GeV. And that's an interesting number that highly constrains many models of beyond the standard model physics, including supersymmetry. Okay, and of course, at run 1, at 8 TeV, the LHC searched extensively for new physics, and this, you can't read this, but anyway, all of these are limits. It's just to give you some view from 30,000 feet of what the sort of scope of their search for new physics, and that it didn't yet turn up anything. Okay, so we all know that. And just recently, just at the beginning of August, we reached another important milestone, which is the first 10 inverse femtobarns at 13 TeV. So the LHC doubled its energy, basically, and collected a decent-sized data set of the same order of magnitude as their previous data set at 8 TeV. So now, with this milestone, the sensitivity to new physics is starting to greatly exceed what was previously there at 8 TeV. Okay, you may have heard the most exciting thing that happened is this 750 GeV resonance, and it's going away, unfortunately. I think if Nima's one of the 3 people in the world that didn't write a paper on it, then I'm the second one. I don't know who the third is, but we'll find him. Him or her. Sorry? Yeah. Okay, so yeah, so that, I'm not proud of that bet. I mean, it would have been great if this had turned out to be real, and that's what probably all of us would be working on if there was really new physics beyond the standard model. So, but all accounts are that it's receding back into the background, into the continuum. And they've searched, again, for supersymmetry far and wide, and still no definitive discovery. So these are some limits on searches for Ino production. So these are the, as I'll review in a bit more detail, these are the largest cross sections at the LHC for a given mass. And so when they decay, they produce many jets, and they can produce missing energy. And so they've searched for many jets and missing energy and set some limits on the Ino mass, which this is in a simplified model in the gluino neutralino mass plane. So assuming there's just 2 superpartners in the spectrum, and this is literally what they look for, then they set a limit in this 2-dimensional plane, which has this characteristic shape that turns over as you make the neutralino heavier. And so if the neutralino is massless, then there's the largest jets and the most missing energy, and the limit goes up to nearly 2 TeV. This is the same sort of search, but for squark production. Here you have fewer jets, but still missing energy, and so they can set limits also on squark production. And this is a very well-motivated search, as I'll explain in a moment. This is a search for the stop squark, the superpartner of the top. And this is a particle that would be expected to be light based on the naturalness criterion. And again, here they saw nothing, and so they set limits that go up to a TeV for a simple model where the simple spectrum where the stop decays directly to a neutralino plus a top. And so these are the limits, both Atlas and CMS see limits that go up to 900 or so GeV. And so basically no definitive evidence for supersymmetry yet, but here there are actually some interesting fluctuations that personally I'm interested in. And because they're very well motivated, and they're kind of seen in both experiments. So these dashed lines are the expected limits, and the solid things here, or the solid lines here, are the observed limits. And in both Atlas and CMS, they're a bit, the observed limits are a bit weaker than they expected which signals some small excess. But it's very likely to be just a fluctuation. But if this were real, if this were to grow in the next iteration of their results, namely at Moriond in the spring, that would be very exciting news. And there's even bigger deviations in specific signal regions. The largest one they have is a 3.3 sigma excess in a 1 lepton stop search in a particular signal region. So this is, of course, has to be subject to this look elsewhere effect. But anyway, this is just something to keep an eye on, I think, because if they double the data or triple the data, then this excess, and this excess is real, it'll become quite spectacular in the spring. Okay, so because there was no strong evidence for new physics at ICHEP, people are getting a bit concerned, and rightfully so. And so today I want to explain to you in more detail, what the concern is and what's left, I guess, and how concerned should we be. So, so people are starting to have a little gallows humor about supersymmetry and its discovery prospects. So let me begin by reviewing the naturalness principle and how it applies to SUSY and how that motivates limits, a way of looking at the limits. So as you all know, there's this idea that goes back to Wilson and de Tooft that there should be no small parameters in nature except those that are determined by some symmetry. And when applied to the Higgs potential, then this leads to an interesting prediction that there should be new physics at the TeV scale. So the Higgs potential in the standard model has just 2 parameters, and by now we've measured both of those parameters. And in particular, it has this mass squared parameter, which is actually the only dimensionful parameter in the entire standard model. And so the basic question is, why is that mass parameter where it is at 100 GeV scale and not at the only other dimensionful scale that we know about for sure, which is the Planck scale? Why is it not all the way up there? And the problem, of course, is more acute when you take into account quantum corrections. There are these, if you have new physics at any scale lambda that talks to the Higgs, it could run in a loop, and in the standard model would contribute a quadratic correction to the Higgs mass squared parameter. And if you have many of these particles at different scales, and they all contribute these additive quadratic corrections to the Higgs mass squared, then the puzzle is, how do they cancel? Why do they cancel to, if this scale is much bigger than some TeV scale, then why do they all conspire to cancel and give you, the observed value of this Higgs mass squared? Okay. So so we try to quantify something which is maybe not quantifiable as a way of keeping score and as an interesting way to put the results in context. So that's what I'm going to talk about now, which is a measure for the fine-tuning. It's not rigorous, it's not mathematically defensible, but yet everyone seems to keep coming back to it because it's the only way we know how to make sense of the limits, which are otherwise just abstract limits on masses that just keep marching outwards. Okay, so this is called the Barbieri-Giudice measure for fine-tuning, which is very simplistic and just says if I have a bunch of additive corrections to this mass squared parameter, I don't want any one of them to be much bigger than the mass itself. And so this delta, if it's a very large number, indicates a high degree of cancellation. Okay? And inverse of delta is like a percentage of, or is a fraction, the amount of fine-tuning, the amount of cancellation you have to do. The naturalness criterion in this language would be that you don't want delta to be too large, and in today's talk we'll take delta of 10 to be a benchmark value. And if you plug in delta of 10 and this quadratic divergence here, you find that the cutoff scale should be of order of TeV for an order 1 coupling. And so that's the basic prediction, that there should be new physics at the TeV scale, which has motivated the construction of the LHC and would have motivated the construction of the SSC, is to discover the Higgs and to discover the naturalness particles that should be there at the TeV scale. Okay. And of course, it's not enough just to add particles at the TeV scale. We have to shield the theory from divergences at higher and higher scales, and that requires some kind of symmetry or compositeness or something, and so supersymmetry is one of the main mechanisms for doing that. Okay, so in conventional realizations of SUSY, so SUSY is this very complicated parameter space, and that can be daunting, but what I want to tell you, if you're not aware of if you're not an expert, is that there's really only 3 masses or 3 parameters that you have to keep track of if all you care about is naturalness. And these are the Higgs Ino mass, the stop masses, and the Ino mass. So these three superpartner masses are all that really are the most important things for naturalness. And the reason is that they couple the strongest to the Higgs. They correct the Higgs mass squared parameter the largest. So at tree level already you have the Higgs Ino, the superpartner of the Higgs, which corrects the Higgs mass squared parameter tree level and just contributes quadratically. So basically, if you don't want this to be too large, then the Higgs Ino mass should not be too large. Now at one loop, you have the contribution from the stop, and it's large because it fills the top Yukawa. Okay, so here you also see for the first time the messenger scale, this parameter lambda, will also feature prominently. And the messenger scale is the scale at which these superpartner masses are first generated. And then we have to run the renormalization group down to the weak scale to understand what their effect is on the Higgs mass. And so this is the leading log formula for that. Just from integrating the one-loop RGEs, you get a formula like that. And this is the sign the supersymmetry is working, that what would have been a quadratic divergence in lambda is softened just to a log. Okay? But still, that log is a problem, as we'll see. Then the next superpartner that's constrained by naturalness is the Ino. That's the one that feels the strong force and then the top Yukawa through a two-loop diagram like that. And so the Ino is also strongly constrained to some extent by naturalness. Okay, so I've written them in this order because this is the most constrained, this is the next most constrained, this is the second next most constrained. And so if they were all right up at their naturalness bounds, then you would expect them to be in this hierarchy. Ino's heaviest, then stops, then the Higgs Inos. Okay. Now the perverse thing about the LHC, or any hadron collider for that matter, is that it produces them in the opposite strength. So it produces Inos with the largest cross-section. It's most sensitive to Inos, yet they're the least constrained by naturalness. So if we really wanted to build naturalness testing collider, we would have built a Higgs Ino factory, which would have been, I guess, an E plus E minus type machine. Anyway, so we do what we can with what we've got, and so these are some cross sections at 8 and 13 TeV for Ino production. You see they're the largest here, or in red, just Ino production, and then next stops are several orders of magnitude smaller, and finally you have Higgs Inos, or electroweak Inos, several orders of magnitude smaller than that. Okay, so now. The naturalness bound on Higgs Ino mass is the simplest to state because everything was just at tree level. So basically, if you don't want the theory to be more than 10% fine-tuned, the Higgs Ino should be lighter than about 300 GeV, which is, you would think, well within reach of the LHC. But unfortunately, due to these low cross-sections and the high background coming from QCD, these light Higgs Inos can be very difficult to see. Currently, the limits do not surpass LEP and may never surpass, well, it's going to take them a long time to actually surpass LEP. So we don't know. There could be a Higgs Ino sitting there at 100 GeV, and it may take us a long time to know that. Okay, so that's already something to keep in mind when people tell you that there's no chance for discovery, new physics at the LHC. Now we come to the Ino, and so here are some limits on the Ino mass as a function of the messenger scale for different choices of this fine-tuning parameter. So for instance, if we take delta of 10 to be a guide, then you see that the Ino should be lighter than some amount that depends on what the messenger scale you choose to be. And the messenger scale a priori could be anywhere between 10 TeV and the gut scale. And conventionally, there's been a lot of focus on high-scale models. But as you can see, that makes the fine-tuning considerably worse. This dashed line here is that most naive Ino limit that I showed you earlier, just to set the scale. So if that were completely true, then all that's left would be the lowest messenger scales. Okay. So I don't think I have time to explain this technical side, but in this work that's going to come out, we've taken into account some precision effects that actually significantly relax these the fine-tuning due to the Ino, and this is a benchmark value for the Ino bound coming from this paper from 2011, and we can improve the fine-tuning by, or the limit on the Ino by more than a factor of 2. Okay. Similarly, naturalness also bounds the stop as a function of the messenger scale, the stop mass. And if you take delta of 10 to be your reference, then again, you're forced to live at low messenger scales. And this is the typical limit on the stop mass coming from the current searches. Okay. So, of course, this is hopelessly naive. And so the work that we're doing is to investigate this in much more detail. Okay. So what we'd like to know is what are the implications of the latest ICHEP results for supersymmetric scenarios motivated by naturalness, where there's light gluinos, light stops, and light Higgs Inos. And because the LHC searches only set limits on a handful of scenarios, there are many cases, basically all the cases, where they aren't directly setting limits on the natural SUSY motivated scenarios that we're interested in. So in order to understand what their null results mean, we have to do a fair amount of work, which these days goes by the name of recasting or reinterpreting their results. And so that requires a fair amount of simulation, which if we'd all installed Pythia in 2005, then maybe we'd all be doing that now. But anyway, this is the nitty-gritty of it. This is what passes for calculation in this area. So you have to simulate the signal, basically some 2-to-2 Feynman diagrams, and Monte Carlo that, and then shower and hadronize them using some standard packages, and then a key point is to then cluster those things into jets and identify objects, electrons, photons, muons, and so there's a detector simulation. And then one has to take the existing searches, they publish their cuts, and they publish the backgrounds, and so one has to recast those searches, compute the signal efficiencies, and understand what the limits are on the scenario of interest. Okay. So that's what we've been doing since the beginning of August. And these are the searches we've recasted, which basically summarize, from past experience, these are expected to be the most relevant searches for any natural SUSY scenario that you could come up with. These are jets plus MET type searches. There's several variants of those. These are some searches involving leptons, and then these are searches that don't involve any missing energy at all, and will pick up scenarios, natural SUSY scenarios, where you don't have any missing energies, like if you have R parity violation. Okay. So using these searches, now we can proceed to investigate what's left for natural SUSY. So I'm going to phrase it as a series of different simplified, what are called simplified models or simplified spectra, basically, which we've chosen to be representative of a wider class of models and attempt to be fairly comprehensive and not make any model-dependent assumptions that we can avoid making to sort of cover all of the signature space of natural SUSY. That's the idea. And so the first scenario is our baseline scenario. This is what we've called vanilla SUSY, where it's probably what everyone would have liked to have seen before the LHC turned on, which is the MSSM with R parity to eliminate many, many couplings, and then flavor degenerate squarks and sleptons to eliminate all the flavor problems. So this would be the simplest, nicest model that could have been seen, certainly the most minimal. And it's an essential, even though, as I'll explain, this model is quite dead from the point of view of naturalness, this is an essential baseline model because everything else is sort of built on top of this as some epicycle or another. All right, so this vanilla SUSY has two important consequences for the collider. With R parity, the LSP is exactly stable. So it gives you, if it's charged, then you're pretty much dead. And if it's neutral, then it escapes the detector's missing energy. And then with flavor universality, that you assume to avoid flavor changing neutral currents, then if the stop is light due to naturalness, then up and down squarks are also light due to the flavor universality. And because the proton is made out of up and down quarks, these up and down squarks have an enormous production cross-section through this T-channel diagram. So this turns out to be a real problem for this scenario. Just to illustrate that, this is the cross-section computed using some public code and at 8 TeV, but it's also true now at 13, showing the up and down squark cross-section versus compared against just that of a single stop, and it's over 5 orders of magnitude larger, and this proves to be very difficult to hide now at the LHC. Okay. So this is our recasted limits on the vanilla SUSY scenario. In the gluino and squark mass plane, we fixed the Higgs Ino mass to be at its upper bound for naturalness of 300 GeV, but the results don't really depend on what you choose for that. So these are the old limits from 8 TeV, and these are the new limits, the strongest limits shown only here. And then this is the region that was 10% natural or better with a very low messenger scale of 20 TeV. So already at 8 TeV, you were more than 10% fine-tuned, and now, well, I didn't show it, but now you're probing the 5% fine-tuned region. Okay, so that's not looking good. But actually, there's an even bigger problem with the vanilla scenario, which is the Higgs mass. That I won't have time to talk about much, but I just want to bring your attention to that, which is that the value of the Higgs mass being 125 is a serious problem for the MSSM, which is a part of this vanilla scenario. In the MSSM, there's a famous tree-level bound saying that the Higgs mass should be lighter than mz, and to get beyond that, you need, which is 90 GeV in case you were wondering, to get beyond that, you have to add in some loop corrections, the biggest ones of which come from the stop sector at 1 loop. And so in order to get to 125, it turns out these loop corrections need to be quite large. You basically need to double the mass squared to get to 125. And so that implies the stops are very heavy at 10 TeV or more, or these A terms, these trilinear A terms, are very large at multi-TeV. So either way you look at it, the MSSM with the Higgs at 125 is more than 1% fine-tuned by this measure that we wrote down earlier. Okay, so basically vanilla SUSY cannot be 100% natural anymore, and it's being constrained. I mean, its naturalness is being limited on both sides independently by the 125 GeV Higgs and by the direct searches. And so that's where we are with vanilla SUSY. So, and it could always just be that we got unlucky and there was a percent level accident or more in how the Higgs mass squared was determined. We may never know, especially if we don't get to build another collider. So, but that's considered to be the ultimate FU scenario. If nature wants to be very cruel to us, that's what it would do. So, and it also doesn't give us much to think about. So, as far as coming up with sort of signatures for the collider to continue to probe, we're motivated still to think about alternatives to vanilla SUSY that that could be more natural and have lighter superpartners, et cetera. Okay, so that's what we're going to explore in the rest of the talk. So maybe it's not vanilla SUSY, maybe it's not the most minimal thing we could have come up with. After all, why should it have been that way? There's many other flavors of supersymmetry you could consider. My personal favorite is Cherry Garcia. There's many non-minimal possibilities, and that's sort of where you're forced to these days if you want things to be fully natural. And okay, so I obviously don't have time to review all the different ideas that people have had for going beyond vanilla SUSY to solve these various issues, but you have to address the Higgs mass problem and you have to address the collider constraints. That much is clear. So what I want to focus on today are just the collider constraints and how they influence non-minimal models of natural SUSY. Okay, so one idea that's very nice that people have had is the observation that the first and second generation squarks, these were the ones causing the problem for the collider constraints. These are the ones with the huge cross sections, but they're not actually required for naturalness. You may have noticed they're not stops, basically. And so perhaps one could imagine that the boundary condition at the messenger scale is such that they're decoupled, or just, they don't have to be decoupled from the LHC. So in practice, maybe 5 TeV or something. Then then they're not produced at the LHC, and the limits could be much weaker. There are still limits, though, on direct Ino production, which we've recasted to be about 1.8 TeV or so, 1.7, 1.8 TeV. But this is the 10% natural region here, and so there's still quite a lot of parameter space left that could be fully natural. And the stop searches are also in effect, putting you at a TeV, still there's room to be fully natural. Okay, so that's, if you were just to do one thing, that would be the simplest thing you could imagine doing. And actually, but that does limit you to very low messenger scales, which is an interesting constraint for future model building. It's not clear how many models there are of this type, and what we know about them. Actually, Nima, I think, mentioned yesterday at dinner, or was it in today's talk? I don't remember now, about some models that he had built of composite direct mediation, which might actually be relevant here. So, okay, so that's sort of the implication for this class of models, that maybe the first and second generation squarks are heavier than the third generation, that they're not all flavor degenerate, and the messenger scale is very low. And so that brings me to one point of contact with Nadis' previous work, which was perhaps, so this paper maybe have a lot of foresight, which was they were trying to ask exactly this question: should the squarks be degenerate, and by how much, based on flavor constraints and based on models that would generate the Yukawa couplings, whether you could generate the Yukawa couplings and also generate the squark masses, have them be aligned, but not degenerate. So this is exactly the sort of idea, I think, that's highly well motivated now after the ICHEP results. Okay, so let's see, okay, good. So the next scenario, so you can try to decouple the first and second generation squarks. That reduces the SUSY cross-section, that reduces the strength of the limits considerably. The other obvious thing you can try is to get rid of the missing energy. And so if you take away R parity conservation, then by turning on these R parity violating couplings, then your LSP can decay, and if you make it decay to jets, if you make it decay hadronically, then that proves to be very difficult to see, because now you don't have as many handles to distinguish this from QCD if it's all hadronic. And so this is an example of that, showing if you have RPV but still flavor universal squarks, then these are the limits coming from Atlas jets plus MET searches and an Atlas no. So this is an Atlas 8 to 10 jets plus very little MET, and this is an Atlas no missing energy search. They set the strongest limits, and the previous ATV limits are here. And so you see that the 10% natural region with a very low messenger scale has a little bit of a wedge surviving after these limits. Okay. So at ATV, this used to be very promising, this mechanism of just getting rid of the missing energy. But after the ICHEP results, I would say if you only add this one epicycle of RPV, this is less promising. Okay. If you combine both a MET for jets mechanism and decoupling the first and second generation squarks, that has the best, obviously, so you do two things that separately hide SUSY, then that has the best prospects still for being natural. You have this entire parameter space stretching up to gluinos of 2.4 TeV and stops at 1.4 TeV. That it'll take, as I'll review at the end of my talk, it'll take them quite a long time to get out to here. Okay. Of course, if we just happen to live right here, that would be a very strange situation and some kind of fine-tuning that we're not taking into account, I think. Okay, so yeah, so anyway, but something which emerges from all this is that only the lowest possible messenger scales can be fully natural now. Okay. So now in my remaining few minutes, I just want to say some less detailed comments about how much discovery potential for SUSY remains at the LHC. So what's in store for the future. And one thing which I think it's important to appreciate is on the negative side, is that I think we're entering the slow phase of the LHC. So this is some slides I took from an expert on this from last year's Morion conference, showing the expected data set they're going to collect next year, and then, well, I guess 2018, there's some shutdown. But anyway, they're going to, and maybe these numbers are roughly constant at 30 to 40 30 to 50 inverse femtobarns. And the integrated luminosity, or the peak luminosity, peak instantaneous luminosity, sorry, is going to also level out at about 2 times 10 to the 34 inverse centimeters squared inverse seconds. And so this peak integrated luminosity is some measure if you integrate it over the, peak instantaneous luminosity, if you integrate it over the amount of time they run, gives you some measure of the data set. And you see that that's basically leveling out, and it's going to be that way all the way till 2023. So we've entered the linear, and the energy is basically fixed at 13 or 14 TeV. So we basically entered the linear growth phase of the LHC. Prior to that, we were always on a faster than linear growth phase. And so the results are going to, and the limits are going to grow more slowly. And so here's a plot illustrating that, where we projected the ATV limits to now and then to the future based on some very simplistic assumptions that they're governed by parton luminosities and scale like 1 over mass squared. And that actually turns out to work almost unreasonably well. It basically assumes that everything the experimentalists do is going to be optimized and as good as it is now, and it's going to continue that way in the future. So you see that here were the ATV limits on gluinos in the most optimistic case, or in the best limits that they got. And these are the current limits, which match the projections very well. And at Moriond next year, they're going to only grow by 100 GeV or so. And it's going to take, so it's about 50 inverse femtobarns a year until you get to here. So this is like the next 7 years. And the limits are only going to grow by maybe 200 GeV. And then this is the high luminosity era, which we've compressed onto a log scale. Otherwise, you wouldn't even see this here. And in the high luminosity era, they're expected to get 300 inverse femtobarns a year. So this is going to take another 10 years to grow the gluino limit by another 200 GeV or so. Okay, so it's going to be very slow, the march of progress. But on the positive side, if you measure relative to the ATV limits, we've only covered about half of the eventual reach. So there's half more. There's twice as much reach left. It's just going to take a lot longer. And these are limits also. So if there's going to be a discovery, there's still quite a lot of discovery potential left because it has to grow. Basically, it might scale like square root of luminosity, and still we've collected only a tiny fraction of our data set. So there's still lots of opportunities for some tiny fluctuation to grow into 5 sigma. Okay, these are the stop projections. And here, because of these upward fluctuations that we've been seeing, we haven't quite reached our full potential, and the march of progress could be a little bit faster for the stops. But basically, once you turn on the machine at a higher energy, there's this rapid jump in mass reach, and then a much slower growth phase after that. So we're reaching that shoulder now. Okay, and of course, these are all the most optimistic or the most naive limits, and if you do, you can easily make the limits much weaker. Here's a particular arrangement of the sparticles that show you that the stop could still be as light as 500 GeV, much lighter than the 1 TeV limit I was presenting previously. And so these scenarios are going to require more data and possibly better analysis techniques, so we could see more progress there. Okay, so I'm just going to wrap up because I'm out of time. Everyone wants to know, is it time to panic? And I'm not talking about Donald Trump. So we're talking about the LHC, right? Is it time to panic? And I think it's certainly, SUSY could have shown up by now, but the fact that it hasn't doesn't mean that it's not there, even if you are very strict about naturalness, I think. Certainly things could just get heavier and heavier and more fine-tuned, and we may never know. But even if you're a real naturalness aficionado, you know, it just from the fact that it hasn't showed up yet doesn't mean that it's not there. Okay. That being said, as we've seen from all the plots I've shown, natural SUSY is under severe pressure from both the LHC searches and from the Higgs mass being what it is. And if you believe in fully natural SUSY, then you probably shouldn't be eating vanilla flavor anymore. You should try something else like strawberry or chocolate. And so yeah, so that's the main message, I guess, is that many other flavors of natural SUSY are still viable beyond the simplest thing. And so you could take that as an epicycle and say, I'm going to stop caring, or you could say, well, the standard model is far from minimal, so why should we expect the next layer of reality to be minimal? So we won't know which one is correct until we keep running the machine. So some things that we explored here that are still viable include decoupling the first and second generation squarks and trading missing energy for jets. One thing that's clear from all these simulations that we've done is that if it is going to be fully natural, it has to have a very low messenger scale, absent any UV magic that we're not taking into account here. But if there's no UV magic, then the messenger scale has to be extremely low. That's my timer saying it's 45 minutes. Okay. And so, but certainly if SUSY exists and is fully natural, it's certainly not what most people envisioned before the LHC turned on. And so I think it's too early to give up, but maybe the timescales are going to stretch out a bit going forward. Unless one of these fluctuations I mentioned at the beginning grows, the data set is still going to double or triple by next spring. And so natural SUSY and new physics more generally could still be around the corner. We've looked in most of the obvious places, and even if we just keep doing that alone, there's still plenty of time for a fluctuation to grow into a discovery. And also there exist many more challenging signatures in less obvious places that people are still continuing to explore every day that will require more data and more sophisticated analysis techniques. So with only just a few percent of the LHC data set and even smaller percentage of the high luminosity data set collected so far, there's still much discovery potential. So it's way too early to give up. The score is 0 to 2, but it's only the halftime or something. I think I learned that sports analogy from Nadis maybe. Okay, I don't. Yeah, but it could take much longer, and so maybe don't hold your breath, although you never know. But hopefully we'll have discovered supersymmetry at least in time for the next time we all gather to celebrate Nadis' birthday. Roughly 10 years from now. I had to make it a multiple of 6 so I could put two more hexagons on here. So looking forward to celebrating Nadis' next birthday together with the discovery of SUSY. Thanks.
So it's hard to assign probabilities for a one-time thing, but if 538 was interested in these scenarios, what do you think the odds would be for the various scenarios there?
Various scenarios that I've come up with. Well, I think our parity violation is a little bit contrived. The couplings are highly constrained, so I think if I had to bet, it would. Well, you're just talking about with the Bayesian prior that it's supersymmetry. Yeah. Then if within the realm of supersymmetry and naturalness, I would say decoupling the first and second generation quarks works pretty well. And that's an interesting model building challenge to think about. There are other scenarios that trade missing energy for hadronic stuff, like something called stealth SUSY that doesn't require R parity violation. And also hidden valleys don't require R parity violation. So it could be that as well. So I think there's still many possibilities left. Yeah, there's so many possibilities that it's like the Republican field before the primaries. It was hard to assign a probability to any one. Although I heard that some people tried and lost when they bet against Trump. So, okay.
Okay, so right now you described the LHC program to go from 300 inverse femtobarn to 3,000. If you had the power to decide, would you recommend to go from 300 to 3,000, or would you rather make an effort to increase the energy?
Well, I don't have that power, and it's very hypothetical, and I haven't thought about it so as deeply as the professionals who give these kind of talks at Morion. Also, the needs are different, I think. There's a precision standard model program at the LHC that requires 3 inverse atabarns probably to measure the Higgs couplings more precisely, et cetera. That's not something I work on, and that would be another avenue towards, towards seeing if there's new physics or not. That's completely orthogonal to this direct search philosophy. But as far as direct searches are concerned, I'm not sure there's much difference between 1 or 3 inverse atabarns and doubling the energy by installing better magnets. Sure seems like a nice idea to me.
You're being way too nice, but I
Yeah.
Yeah, this.
That's a double negative claim.
Oh,
But you said that in the subordinate clause, you said that installing a higher magnet sounded good to you.
that's what I meant to say. Yes, yeah. By the way, that's a proposal on the table, although I think high luminosity era is pretty much a done deal, at least to one inverse Atabarn. And the DOE's committed money to that, and people are building the components for it, et cetera. But there is an alternative proposal, maybe after an inverse Atabarn, to if the magnet technology improves, they could just take out all the existing magnets and put in the new ones with the existing tunnel, and that would just up to double the energy of the LHC. It's not that easy. It would be very expensive, but and take a lot of time. But they could do it, I think. Yeah.
Yeah, this must be a very stupid question, but I mean, there are all sorts of searches being done within CMS and Atlas. So how does your recasting analysis differ from what those guys are doing?
Oh, okay. That's a good question. So I went over it very quickly, but these are all existing Atlas and CMS searches. You notice that we've mostly focused on Atlas, and there's only a couple CMS ones. The reasons are technical, and I don't want to get into it, but basically they've all done searches in these channels, Jet plus Med, et cetera, and all we've done is taken, I mean, it's a lot of work, but what we've done is taken their original analyses and simulated them and reinterpreted them in terms of our new physics models. Now, there are many, many more searches here. Yeah. Exactly. So they've done these searches. They have expected number of events and the observed number of events, and then they set limits on a very limited set of theoretical scenarios. So you can't immediately carry those limits over to your favorite model without doing all this extra work. Now you might have been asking about all the other searches that they've done, like the giant summary plot I showed you before. That was for 8 TeV, but there's a similar one at 13 TeV. So what about all those searches? So the assumption here is that these are the most relevant ones for the scenarios we're interested in, motivated by natural SUSY, and that have lots of jets and missing energy, or just more jets and leptons, et cetera. So there's other even more exotic scenarios that they've looked for that, if natural SUSY scenario were to do that, they would have seen it too, so we didn't bother recasting those in. That's not how you would hide SUSY, probably. Yeah. Thanks.
Okay, let's thank David again.